This is podcast 5.3 for AP Chemistry. We're going to talk about colligative properties of solutions. So the first thing you need to know is what those three colligative properties are. And they're boiling point elevation, freezing point depression, and osmotic pressure. Those three properties are affected only by the number of particles, not by the identity of the solute particles that we have. So for example, if we have sugar versus salt, the identity of those doesn't matter. What does matter, though, is how many particles there are. So we're going to use that idea of the Hoff factor again. If it's an ionic compound, we're going to split it up into the number of particles that there are. So boiling point elevation is when we have the addition of a non-volatile solute. And remember, a non-volatile solute is something that doesn't go into the gas phase. So sugar, salts, it's some sort of solid that won't add to the vapor pressure. When we add those things, it elevates the boiling point of the solvent. So instead of water boiling at 100 degrees Celsius, maybe it boils at 100.5 degrees Celsius. It depends on what we're adding and how much we add of it. Here's the equation that we can use to figure out that change in temperature from the boiling point. So delta T, and then Kb is a constant. You're going to look it up. It's on page 505 in your book. There's a table. It's a table 11.5, and you can look it up for all the different solvents that we're going to use. Of course, the most common one's going to be water. And then the little m is the molality of the solute. So the solute is what we're adding to the solvent. And the molality, remember, is moles of your solute per kilogram of your solvent. So those are the three parts to the boiling point elevation calculation. Let's see if we can do a problem here. So a solution was prepared by dissolving 18 grams of glucose in 150 grams of water. The resulting solution was found to have a boiling point of 100.34 degrees Celsius. Calculate the molar mass of glucose. Glucose is a molecular solid that is present as individual molecules in solution. The reason they told us this last part is so that we know glucose is not ionic, so it's not going to split into more than one particle. It's just going to stay as one particle. That way we don't have to worry about ionic compounds. But what we're going to do first is we're going to use that formula that we just talked about. This is of the solute. So the first thing we need to know is Kb. They did not give us Kb, but if we looked it up in that table that I was talking about on page 505, the Kb for water is 0.51 degrees Celsius kilograms per mole. Make sure you use the correct one. There's a Kb and a Kf. Kb is for boiling point elevation. The Kf is for freezing point depression. So there we go. Let's see, what else do we have? They gave us enough information so we can calculate delta T. Delta T we know for water, and it also tells us in that same table, the normal boiling point for water is 100 degrees Celsius. But they told us that this solution boils at 100.34 degrees Celsius, so we would just subtract those two to find delta T. We know Kb. What we're going to solve for is the m. That's what we don't know. So I'm going to have 0.34 degrees Celsius, that's the change in temperature, is equal to 0.51 degrees Celsius kilogram per mole. And I'm going to solve for the molality of the solute. So when I do that, the molality of my solute comes out to be 0.667 moles, and because this is glucose, this is the solute, I'm going to add that in, per 1 kilogram of the solvent, which in this case is water. So that's what we just found. And then what we're going to do, because we know that we're looking for grams per mole, that's the molar mass units, I'm going to take the information that they gave us in the problem, and I'm going to look for grams of glucose per kilogram of water. Because if I can get both denominators to be 1 kilogram of water on the bottom, I will know how many grams and how many moles are equivalent in the same amount of water, and that's a way that I can divide and then end up with our molar mass. So I'm going to take the 18 grams of glucose from the problem, and I'm going to divide it by the 150 grams of water. But I'm going to do a quick conversion because I would rather have that in kilograms to match this one. So this is going to be 0.15 kilograms of water. So if I take 18 and I divide by 0.15, I end up with 120 grams of glucose per 1 kilogram of water. So I have this value and I have this value. And since both of them have the same denominator, I know that there must be 120 grams of glucose per 0.667 moles of glucose. So I can do the grams divided by moles with these two values, and I'll end up with the molar mass. So 120 grams divided by the moles is going to equal the 180 grams per mole for the molar mass. So the first thing we did was we solved for molality using the information from the problem, and then we kind of left that alone for a second. Then we went back up into the problem and we looked grams of glucose per grams of water, and I converted that into grams of glucose per kilogram of water to match my molality. And then I was able to take my grams and my moles and divide them to come out with the molar mass. Okay, so freezing point depression looks a lot like boiling point elevation. Freezing point depression is the exact same formula. We have the change in temperature, but this time it's the change in temperature from the freezing point. We have a KB, that should not be KB, that is a typo. That needs to be KF for freezing point depression. So change that B, this should be KF, and then M of the solute. Oops, yep. And then delta T. So we have the change in temperature from the freezing point. We have our constant again, which we're going to look up in the same table. And then we have the molality of the solute. So same formula, just a different constant. What we find is that when we put a non-volatile solute into a solvent, just like we were doing with the boiling point elevation, this lowers the freezing point of the pure solvent. So this is why we can add ice or add salt to ice, and it will melt the ice, because when we add that salt, it lowers the freezing point of water to the point that it turns back into a liquid and will melt. And the reason that the freezing point depression and boiling point elevation work is if you have your water molecules, since water is the most common solvent, we'll use it as an example. When you introduce a new solid, say salt, the salt and the water start interacting with each other, which will make it harder for the water molecules to freeze because they have to now overcome the force of attraction between the salt and the water molecules. And it will also make it harder for the water molecules to escape to the gas phase, which is why the boiling point elevation goes up. So when you're putting in the solutes, it's adding this new aspect of there's new interactions going on between the solute and the solvent. So that's why the boiling point goes up and the freezing point goes down, because you're adding a whole new set of intermolecular forces between the two different molecules. Okay, our next example problem is using the freezing point depression. And it says what mass of ethylene glycol, and it gives us its molar mass, the main component of antifreeze, must be added to 10 liters of water to produce a solution for use in a car's radiator that freezes at -10 degrees Fahrenheit, which is the same as -23.3 degrees Celsius. And then assume the density of water is exactly 1 gram per milliliter. So the first thing I'm going to do is I'm going to remember what formula we're using here. And just like we did in the last problem, I can look up KF and I can figure out delta T. I'm going to solve for the molality of the solute first. So delta T in this case, because we're talking about water, we're going to say is 0 minus a -23.3 degrees Celsius. So that'll end up being 23.3 degrees Celsius is equal to the KF, if we look it up for water in that same data table, is 1.86. So that's equal to 1.86 times the molality of the solute. So if I do that, my molality ends up being 12.5 moles of ethylene glycol, and I'm just going to abbreviate that EG, per 1 kilogram of water. So what I'm going to do this time, though, is they're not asking me to find the molar mass, so I'm not going to use this and try to rearrange to get kilograms on the bottom again. I'm going to use this now as a conversion factor. I'm going to do just a big dimensional analysis problem, and you'll see how this works out. So the first thing I'm going to do is I'm going to start with the amount of water that they told me. They said I have 10 liters of water. So I start with my 10 liters of water, and because this is not a mass, they had to give me the density so I could go to grams. And here's the density right here. So because it's in milliliters, I need to convert really quick. So 1 liter is 1,000 milliliters. And then I know that water is 1 milliliter and 1 gram for the density. So now into grams of water. I can use this conversion factor to get me into moles of ethylene glycol, which would be good because eventually I need to end up in grams of ethylene glycol. So 1 gram of, this is water. I know that this is the same as saying 1,000 grams of water on the bottom here. So that's how I'm going to use it so it cancels with this guy. So 1,000 grams of water is what we would find 12.5 moles of ethylene glycol in. So this molality allowed us to go from water to ethylene glycol. Those will cancel. And then they want grams of ethylene glycol. So 1 mole of EG has a molar mass of 62.1. And that's it. I punch that into my calculator, and I end up with 7,760 grams. Quite a bit. Probably wanted to write that in scientific notation for kilograms because it's such a big value. So there's your answer. This time, instead of rearranging what was given and then dividing grams by moles, we used the molality as a conversion factor to take us from the water to the ethylene glycol, so it allowed us to switch substances. Here's just a visual diagram so you can see the changes in boiling point and freezing point specifically of water. The normal freezing and boiling points are I believe they're the purple, and then the blue shows you when we've added a solute, how the freezing point drops and the boiling point goes up. So you can see how it kind of expands the time when we would see a liquid. This is one of those phase diagrams, and then you can calculate the delta TF or the delta TB based on what you're looking at. But you can see how the freezing point goes down and the boiling point goes up. All right, osmotic pressure is the last colligative property we're going to talk about. And osmotic pressure deals with the idea of osmosis. And osmosis is the flow of a solvent into the solution through a semi-permeable membrane. And I'll show you a picture of what this looks like in just a second. Here's the formula that we use. The osmotic pressure is represented by the symbol pi. Big M this time. So big M is molarity. R is the gas constant. And the gas constant we use is this one right here, the 0.0821. And because that has Kelvin in the gas constant, we need to use Kelvin for the temperature. Also making sure that our pressure is in atmospheres so that everything cancels that we need to. So here's a picture that shows osmotic pressure. We have a solution in the flask, and we have a semi-permeable membrane, and then just the pure solvent. So maybe just water out here, that's all we have, and then our solution is something in water. What you're going to see over time, though, is the net movement of the solvent in. It's trying to kind of equalize the concentration, make the concentration in here less to cancel out the difference in concentration. So the solvent moves in, this becomes more diluted, and it's going to get a bigger volume because the solvent's moving into the flask. And then the difference in the height there is your osmotic pressure, because eventually this will stop moving, and that's when it's at equilibrium. Here, the height of the two liquids are identical. It's the same. It's a little hard to see though. That's why we measure the difference in the liquid height here to get the osmotic pressure. So example problem 10, when 33.4 milligrams of a compound is dissolved in 10 milliliters of water at 25 degrees Celsius, the solution has an osmotic pressure of 558 torr. Calculate the molar mass of this compound. So again, they are asking us to calculate molar mass. And so the first thing we're going to do is we're going to use that formula that they gave us. We're going to use pi equals the MRT. And we're going to solve for molarity again. So just like in the others we solved for molality, this one we're going to solve for molarity. They gave us the pressure in torr. So 558 torr, I need to convert that into atmospheres. Divide by 760, and when I do that I end up with 0.734 atms. So that will be my osmotic pressure, my pi. I don't know M, I know R, and then T I can calculate into Kelvin. Just add 273. So plugging this in, I have 0.734 atms equals my molarity times 0.0821 times my temperature, which would be 298 Kelvin. And when I do that, I get the molarity to be equal to 0.030 moles of my compound per 1 liter of my solution. So we're going to keep that boxed so that I remember it's there. The next thing I need to do then is I need to figure out how many grams per liter of solution do I have. So when I look up here, it says I'm adding 33.4 milligrams, which is a very small amount, into 10 milliliters of water. What I'm going to assume then, I'm going to assume that 10 milliliters of water is going to be the same volume as my solution, because the amount of solid I'm adding is really tiny and it's going to be negligible into the volume of the whole solution. So the volume of the water is going to be the same as the volume of my solution. Then all I have to do is take my 33.4 milligrams of my compound, and that's per 10 milliliters of solution. Your milligrams are going to cancel out, so this is really the same as grams per liter. And I need to get 1 liter on the bottom to match up here. So I just divide those two numbers together, and I end up with 3.34 grams of compound per 1 liter of solution. So again, I've got the same denominator, but I have moles on top in one and grams on top in the other. So then to calculate the molar mass, I just take my grams, which is 3.34, and I divide by my moles, which is 0.030 moles. And when I divide those out, I get 111 grams per mole. So that must be the molar mass of my compound. Okay, the Van Hoff factor. The colligative properties of solutions depend on the total concentration of solute particles. That's what we were saying at the beginning, that it doesn't matter what the identity of the solute is, it just matters how many particles of the solute we have. So the Van Hoff factor is an I, and it's the moles of particles in solution divided by the moles of solute dissolved. So really what it's saying is, it's asking if I put in NaCl, 1 mole of NaCl, how many moles of particles will I get? And that would be 2, because it'd be 2 moles of particles in the solution per mole of solute dissolved. So all of these are going to be whole numbers for the expected values. NaCl splits up into 2 ions. Potassium sulfate splits up into 3 ions. We're just splitting up these ionic compounds into the number of ions that make them up. And then when you want to substitute this in to the two different colligative property formulas, and this is the same for boiling point and freezing point depression. You just plug that little I in right before both sides of the formula. So osmotic pressure is equal to the Van Hoff factor times molarity times the gas constant times temperature. And then the change in temperature, whether it's the boiling point or the freezing point, is going to be equal to the Van Hoff factor times that constant times the molality of the solute. So we assume ionic compounds dissociate completely, which is why we were always getting those whole numbers, but this isn't always true. The reason it's not always true is because of ion pairing. That means that when you have really concentrated solutions, not all the ionic compounds, not all those molecules are going to split up. Some of them are going to stay together. All right, so here's our question dealing with the Van Hoff factor. It says the observed osmotic pressure for a 0.1 molar solution of this whole thing is 10.8 atmospheres at 25 degrees Celsius. Compare the expected and experimental values for I. So what we know for the expected is that we just predict how many particles this thing will break up into. And we know that this will come off into one. There's 2 of these and 2 of those. So the expected I should be a value of 5 because that has 5 different ions in it. We can calculate what we actually get though. So the experimental value is going to be something a little different. We're talking about osmotic pressure. So we're going to use this formula, and hopefully they gave me all the information I need because they're asking me to solve for I here. So the osmotic pressure is 10.8 atmospheres, and it's in atmospheres, so that's good. I don't have to do any converting there. I'm looking for I. The molarity is 0.1. My gas constant doesn't change. And then I need to just make sure that temperature is in Kelvin. So I take all those values, and when I solve for I end up with 4.4. So in fact, the Van Hoff factor is lower than what would be expected, probably because of ion pairing. So when they tell you to account for I, you're going to assume, unless they tell you otherwise, that it's always a whole number. But we can see that sometimes that factor is not as high as it should be. Okay, that is it. So the 3 colligative properties, you need to know their formulas, what goes into them, and then also how they affect the physical property of the solution. Make sure you can also account for the Van Hoff factor, so you pay attention when there's ionic compounds that will split into more than one particle when we put them into solution.